Okay, we're going to run through the advanced higher paper, the prelim paper for 2025. I figured the best way to do this would just be to hit record and go. So if there's any mistakes or if there's anything that I'm tripping over, you're seeing it all in real time, just like you would if I was going over it at the front of the class on the board. But with the obvious added advantage of, if you want to skip past something because you don't need to hear it, by all means, please do so. As long as you're writing things down that you need to and you're filling in any evaluation material that you've got in front of you, or make your own, it's up to you. But I'm going to run through the full thing and probably ramble as I go, so feel free to listen to the full thing or use it as efficiently as you need to, as long as you know how to do every question by the end. Okay, so I'm just going to write this on the sheet as I go, kind of thing, explaining anything that I feel like I need to. If I feel like it's particularly easy content, I might just direct you to where you might find information on the surrounding material, but I'll try and be detailed where appropriate. So just tackling multiple choice first. Question 1 starts from Unit 1. Which of the following correctly shows the arrangement of the 3d electrons in the nickel 2+ ion in this particular compound? So first thing I would say that applies to not just this question, but keywords and phrases in terms of specifics to that unit or that topic are what are going to guide you through what you should be paying attention to in the question. So if I'm seeing 3d electrons in arrangement and I'm given a compound which clearly has ligands attached to the central metal ion, before I even start looking at the count, as in the number of electrons, first thing I'd be looking at is the actual shapes of the diagrams themselves, or the splitting diagrams. So what I mean by that is, if there's ligands joined onto a central ion, C and D can just be ignored straight away. And that's going to factor into your timing and how you approach these questions as well. Why am I ignoring these? These two here have 5 degenerate orbitals. They're degenerate because they're equal energy. And they're equal energy, how do I know that? Well, because they're all along one row. Right, so in terms of this y-axis of energy, they're all the same. I can ignore these because as soon as I introduce ligands, regardless of if they have a charge or not, so if they have, if they're neutral ligands or if they're negative ions, it doesn't matter. If they're coming in and they're influencing the arrangement of the d electron shape, as in they're getting in the way of the axes, I can completely ignore degenerate orbitals because there will be a split. And what you need to remember is there is a significance in what the ligand actually is. So some ligands will split the field strongly, some will split it weakly. That's not a factor to consider here because A and B are split, as in one is higher up than the other, by the same amount. So as long as you clocked that these two can be ignored, then it's these two you need to focus on. So the next task would be, okay, if I'm at nickel 2+, how many electrons do I actually have? Well, that's dealt with in the question as well. Clearly it's 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6. So we need to check the data book to see what's going on there. What you're looking for is the d electrons only, which are not found on that page. Found on that page. Okay, so first thing I'd be doing would be finding nickel itself, which is there. And you're given quite a bit of information, to be fair, but the most important stuff is what's going on with these d electrons and how do we identify which ones those even are on this page. So it's the 16 number, but that's not to say that there's 16 d electrons, there's actually 8. And the shortcut method of knowing that would be the fact that it's the 8th transition metal along in that row. The other way to distinguish that would be if you go along to the first element that is not a d block element, which would be calcium. For that electron count there, the third shell in, I'm just zooming again, 288, and the next element along it goes to 289. So clearly that third number is where the electrons are going to start to add in for the d orbitals in the d subshell. So if I go along to nickel, what I'll find is that there's 2 outer electrons that will be lost first because that represents these 2 s electrons that are on the end in terms of how they fill. So what I'm going to need to account for is that they are lost, but the 8 d electrons that are within that third subshell are retained because it's not the outer ones that are being considered when we're looking at just the 3D, which is this third number. So long story short, to get from nickel to nickel 2 plus, yes, I am effectively going from here to here, but if I'm just reading this off of this page, that would be wrong in terms of the electrons lost for the ionization of this. It doesn't mimic the electron arrangement of iron, it loses the 2 outer electrons, so it retains those d electrons, which would get you to answer B and not A. Why is that? Because there's got to be 8 in total, not 6. So that question is really testing you on, do you know what electrons are lost when you ionize a transition metal? And the answer is, it's the outer s electrons, the 4s, that are lost first, meaning it retains these extra 2 d electrons. So the answer is B for this one. Moving on, question 2 is about equilibrium, mainly the constant and what effect that will have on various properties of an equilibrium solution or an equilibrium situation. So when sulfur dioxide and oxygen react, the following equilibrium is established. So it gives us the equation. It's one way. What are some interesting things to note? Well, they're all gases, so it could ask us about pressure. There's a mole ratio. There's a delta H, which signifies if it's exo or endothermic. In this case, it's a negative symbol, so that means it's exothermic. So it could right well ask about temperature at this point as well, which it does. But we'll read on. Which line in the table is correct if the temperature of the equilibrium mixture is increased? If I increase the temperature, I would be favouring an endothermic reaction, which this is not. So this reaction would start to go backwards. So the first thing that we're asked about then is, what effect would that have on K? Well, if the reaction is then going to be forced back the way, K is going to decrease. Remembering that a 50-50 distribution would really be somewhere around K equaling 1. Anything less than 1 is going to go back, anything greater than 1 is going to favour the forward reaction, generally speaking. So in this case it's going to decrease, because this is not an endothermic, it's an exothermic reaction. You'll know that from higher chemistry, not advanced higher. So that makes it A or B at this point. And then we can use that information to filter through to the next part. So as the concentration is also affected by K, we can then determine what the effect is on the concentration of SO3. SO3 is our product, so if we have just argued that K is going to decrease, well, the concentration of SO3 is also going to decrease because it's going to be moving away towards this left-hand side of the reaction. So whatever concentration we started off with here is going to go down because equilibrium is going to favour that way. So the answer is A for that reason. Oxidation state for question 3. Now when it's asking about this, you will have to figure out the individual oxidation state, which is kind of short term for essentially the charge of an ion within a compound. Although we do write it the other way around, we include the symbol first before the number. And then for this case, the sort of stable ions or atoms that are involved will have a constant charge or oxidation state. So in other words, the hydrogens won't change and the oxygens won't change. So if it wants the highest oxidation state of chlorine present, that is the highest positive value. So it increases just as integers do. So the more negative it is, the lower the oxidation state, the more positive it is, the higher the oxidation state. And in this case, should be clear to see right off the bat, but I'll start with the first one just to demonstrate. If I have a look at A, it's HClO. For the elements of this compound that do not vary in terms of their oxidation state, that would have an oxidation state of +1, and that would have an oxidation state of -2, because of where they're positioned as main group elements. Now you might argue, well, chlorine's a main group element as well. Yes, however, some elements have large enough electron arrangements where they can vary in their oxidation state depending on what they are bonding to. And there's kind of more to that story as well, but for now we'll just effectively figure out what we need to do. So overall, our sort of charge or our oxidation state here is +1, take away 2, so -1, which means to sort of combat that, the chlorine would have to have a +1 oxidation state, because overall the compound has to be neutral, and that goes down right through to D, where obviously O4 would give us a much more negative situation, right? That would be 8- or -8, and that is what the chlorine is going to try and offset. So if we think about it as, okay, H plus O4 would be minus 8. So then overall that gives us so far a charge of minus 7. So the chlorine is going to have a positive 7 oxidation state to balance that out, meaning the answer would be D in this case. Moving on to question 4. Element number 104 in the periodic table is, and then you just have to identify the block that it's in. Should be nice and straightforward. 104 is Rutherfordium, which is down there. This is clearly part of the D block, so the answer is C. That question is as simple as that. 5 is a problem solver. The coordination number of an ionic lattice can be determined using the following equation. Okay, so a bit of processing to do, but it's straightforward enough once we see what we're doing. So we're given radius ratio is the radius of a positive ion divided by that of the negative ion. You can ignore that table for now because that's the results. But we're asked what is the coordination number of zinc 2 sulfide. You simply have to look up the radii of these ions in order to get the answer. And that can be done in the data book, which I will look for now. I will say there will be questions in the exam potentially that ask you to use some aspect of the data book that you've maybe not practiced a lot in class or alongside your notes, or potentially you've never used, right? I can imagine there will be some people who tackled that question having never looked at the ionic radii of selected ions. Fair enough. But know that you should look in your data book in the first instance for data that you need to obtain that you can't figure out. It usually directs you to the data book in those instances, which it didn't here, which is odd. It usually does. Maybe it did and I just cut that out of the paper. I'm not sure. We'll never know. Anyway, so we're looking for zinc 2, because that is our positive ion. So zinc 2 in this case would be 74. So we'll note that down. And we'll divide that by sulfide, which is just S2 minus, which is 184. And then we'll figure out a ratio for that just now. So 74 divided by 184, which gives me a fraction, but it equates to roughly 0.4. And I know that that puts me in the range of 0.23 to 0.42. So the coordination number then would be 4, which puts us at answer B. Just based on that table. So you're kind of having to correlate a few things together as you go through that question, but not too difficult. Same can be said for this question actually. So question 6 is sort of asking you to follow along a little story, but the only sort of information you need to bring to the table is an understanding of equilibrium and the equilibrium constant and what that means kind of more physically or more practically within a solution that's at equilibrium. So if we read through it, when substance X is distributed between equal volumes of 2 immiscible solvents, so to translate that, something, X, has been spread out, equal proportions of it, clearly there's 2 things, and they're immiscible, which means they don't mix, so they'll form 2 layers. That's all that's saying. X is made of 2 layers of 2 different things, they've not mixed, so they separate. What are those 2 things? It's water and dichloromethane. An equilibrium will be established, and we're given that equilibrium. When it gives you information like this, with data like this, my advice would be, within a reasonable time constraint, just pause if you can and consider what information you're already being given. What can you extract from that there? Well, there's one compound on both sides, so it's 2 layers. The compounds are different and they're immiscible. It's a reversible reaction, so it's at equilibrium. More importantly, K equals 4. What can you determine from that before you even look at the diagram or read the rest of the question? Well, you can confidently say, because this is significantly higher than 1, equilibrium should at least a little bit favour the right-hand side because of where this value sits relative to 1. So I would expect in the mixture of these 2 immiscible solvents to see more of that compared to that in terms of the concentrations at equilibrium. That's what I would expect, and that's what I'd be predicting will be asked. In the diagrams below, the number of dots represents the relative distribution of X in the two solvents. So essentially what that's saying is the dots represent a ratio. It's just a mole ratio basically, because we're not given it, we're just given X within the equation. So for example, for the first one, A, what it's saying is for every 2 moles of CH2Cl2, we've got 1, 2, 3, 4, 5, 6, 7, 8 moles of H2O. Those numbers are convenient because if I simplify that ratio, that's 1 to 4, which I can then relate to the equilibrium constant. So what this is saying is sort of the opposite of this. I would expect to see 4 moles of CH2Cl2 compared to every 1 mole of water, because that's what the equilibrium constant is telling me. So at that point, I can sort of guess before I read any further that the answer will be B or D, because that ratio in terms of the equilibrium constant holds for these two diagrams. The only thing I don't know is which one is on top and which one is on the bottom, so we'll read ahead. Well, look, it's the next thing. Water is less dense than dichloromethane. Okay, if it's less dense, where will it be? It'll sit on top of the other. The more dense liquid will obviously sink below the other one. So right now it's looking like answer D. Which of the following shows the correct distribution of X between two solvents at equilibrium? We can conclude that it's D because the ratio is correct of CH2Cl2 to H2O based on K. It's literally the only place in the question where I'm getting that information, and I've been clever in that I have simplified the ratio by literally just counting the dots and then dividing by 2. And then I've summarised that it should be 4 moles of these for every 1 mole of these, so it's B or D, and then water is less dense, so it sits on the top, not the bottom. So the answer is D for that question. Not the easiest in terms of time, but if you walk yourself through that question like that, and similar questions like that, like a little story, and you sort of piece things together as you go, you know, sort of crossing off situations as you go, that really should help in terms of breaking down really sort of wordy questions like that. The same shouldn't be said for question 7, right? This is much more of an analytical question, and you should be ruthless in your approach, in my opinion. So what I mean by that is this is about how do you carry something out, and you should know enough to be able to sort of cross things off as we go. So the most appropriate pieces of equipment to use when diluting a solution by a factor of 10 would be, okay, so the first thing we need to think about is accuracy, precision, right? So in terms of precision, we're going from, you know, a 1 decimal place scenario to a 0 decimal places scenario, so they're all the same, so I don't need to worry about precision. In terms of accuracy, that's determined by the equipment that's chosen. So straight away, I'm getting rid of A, and I'm getting rid of C. Why am I doing that? Because they involve using measuring cylinders, which are not the most accurate pieces of equipment in the lab, and you should definitely know that by now. If not, shame on you. You need to make sure that you know that. How would we accurately carry this out? Well, think about it practically. If you're diluting something, you would take a pipette of a concentrated solution, you would dropper that into a standard flask, and then you would fill that flask up to the mark with deionized water, or distilled water if you couldn't get deionized. So it's between B and D, and at this point you're just looking for the correct dilution factor. So 10 to 50 is a dilution factor of 5, 25 to 250 is a dilution factor of 10. So we're definitely going with option D for 7, so not too bad. Question 8 is, again, sort of a bit more knowledge based. Using colorimetry, the most appropriate filter for determining the concentration of green nickel ions, Ni2+, in a solution would be some length in nanometers that obviously corresponds to a wavelength, right? Key fact that we need to remember here, we're considering how colorimetry works, and that the most appropriate colorimetry filter wavelength should be the complementary colour to the solution being tested. Why? This is the wavelength of light that's most strongly absorbed by the solution. So measuring the maximum absorption wavelength, or lambda max as it would be referenced when we performed this at the college, that yields the highest sensitivity and accuracy. So basically we're looking for the corresponding wavelength to the colour that we're working with, as that will be what's absorbed most strongly by the solution. So that's what we want to filter for. So we're going to the colour wheel for this one. Just zoom out now. Got there. Okay. matter. So we're absorbing nickel, so we're looking for a green compound which will absorb the corresponding wavelength of probably somewhere here, which puts us between 380 and 400, so I would expect roughly 390 nanometers to be appropriate. And of the options that we're given, it looks like 390 is the appropriate answer. So for 8, I would be selecting answer A. And then the last one on this page, question 9. Correct formula for tetraamine dichlorido copper, that's a mouthful, 2 complex is one of the following. Now for these, I would take the approach of sort of ignoring the multiple choice options, and sort of work with the name that you've got first and see if you can basically get to the answer without looking at the answers first, and then match it up. And then hopefully the answer that you've written will just match one of the answers that's there. So what do we know about this? Well, first of all, we need to remember what the naming convention kind of means. Obviously the prefix stuff is sort of obvious, right? So tetra meaning how many, amine meaning NH3, etc. So dichlorido, 2 chlorines, or 2 chlorides, I should say. The trickier part to remember is the end. So the name of the metal, and then the charge that's given in brackets and Roman numerals. What do each of these things mean? The most important thing to remember, in my opinion, is these give you different pieces of information about the compound. The copper word, which could have been cuprate, tells you the overall charge of the compound, right, of the complex itself. It only indicates as to whether it will be positive overall or negative overall, or neutral for that matter. So the fact that it doesn't say cuprate suggests to me that it's not option A. Why is that? Because overall it has to be positive or neutral to warrant having the name copper. If it doesn't have that sort of strange Latin root name, cuprate, etc., then it's not a negative complex overall. So I can rule out A. The 2 does not tell me that it's option C, as in the 2 does not indicate the overall charge of the complex. The 2 indicates the charge of the metal ion contained within the complex. So that's what I'm going to have to figure out myself. So if I start writing this down, sort of again, almost ignoring these options, I can see that I've got copper, so I'm going to write that down. Tetraamine dichlorido. Okay, well I'm going to stack the charged ones first, like so, and then I'm going to go for my neutral ligands at the end, so tetraamine. There's 4 of them, so that'll be like so. This contributes no charge, this contributes -1 each, so that's -2. So overall right now it's -2. However, I am told that the copper within this complex has a +2 oxidation state. So if overall the ligands are contributing -2 and copper is contributing a +2, overall the charge of the complex is 0, which leads me to say that 9 is answer B. Okay. And that brings us to the end of the Unit 1 sort of majority content of Section 1. It's now mainly Unit 2, with some Unit 3 thrown in near the end as well, I believe. I might be wrong, we'll find out. Okay, so question 10 gives us straight away a skeletal formula, so hopefully easy straight here. The systematic name of the molecule shown above is, okay, now the first thing I would be suggesting here is clearly it's asking about geometric isomerism, so there's going to be either a cis or a trans isomer present. Before we get to that point, I would suggest that you tackle the systematic naming first. Now, for you, that could mean one of 2 things. You might be very confident and just going straight ahead and using the skeletal formula to get straight to that word, and that's fine, that's great, happy for you. If not, you might want to write that out as a full structural formula. There is absolutely no shame in that. In fact, I would probably encourage you to do it like that, but for the purposes of this question, I'm just going to go straight into using the skeletal formula first, so that we can get to the more important geometric isomerism part. So if I'm looking at this, longest chain is 1, 2, 3, 4, 5, 6 carbons. So straight away, I am getting rid of options A and B. Why? Because they are forms of but-2ene. So for the less intelligent individuals that chose those 4 carbons as the longest chain, which would not be correct. So it's clearly some kind of dimethyl hex 3-ene and the methyl groups are on carbons 3 and 4. If you struggle to follow that part, you need to go away and you need to practice systematic naming. It's not an advanced higher problem you've got there, it's a Nat 5 problem. Okay. Cis and trans wise, I'm looking for the functionalities or the common groups essentially to be on either the same side or different sides. Clearly this is a very symmetrical molecule. The two larger groups are on the same side of the double bond. That is to say, if I split the double bond down the middle, those two groups, I would find, well, if I split it like this, they're on different sides. If I split it like this, they're on the same side. So we need to be confident in which direction we need to split when we're talking about splitting through a double bond. When we're talking about geometric isomerism, we're going through the bond. We want to know what is on the same side of the double bond in terms of a reagent coming in to react with a molecule. So for example, if we talk about this in real terms, why this is important or useful, if I was taking, say, this molecule to do an addition reaction, I would be interested in figuring out, okay, something's going to come in and react. So let's keep it easy, let's say it's Br2. A molecule of Br2 is going to result in something coming in and attacking it from a given side. We know that from our sort of mechanistic organic chemistry. So when I'm talking about the same side of an organic molecule like this, I need to split the double bond down that way, right? Not this way, because then I can see, okay, what's going to happen relative to this side and relative to this side, because these are the directions of quote-unquote attack from another molecule, or these are the directions where something else will interact with this molecule. So that's the way that you need to split the double bond. You need to sort of unzip it, if you like, through it. So if we look at it like that, it's clearly a cis isomer because the functionalities relative to that splitting are on the same side. So the answer would be C for 10. For question 11, should be straightforward, although much like sort of GFMs and stuff like that, this is where daft mistakes can crop in, so we need to be careful. The structure of 2-furanitrile is shown, the number of pi bonds is. So remember, for pi bonds, we are literally just counting over and above single lines. So we have 1 pi bond for every double bond, we have 2 pi bonds for every triple bond. I can do this very quickly, right? 1, 2, 3, 4. The answer is C. Done. Question 12. The structures shown below are isomeric amines. Okay, one is trimethylamine, one is ethyl-methylamine. Which line in the table is correct for trimethylamine when compared to ethyl-methylamine? Okay, so we're looking at boiling point and solubility in water, and what we need to bring in here is the difference between tertiary amines relative to primary and secondary amines. So what is it so special about tertiary amines? Tertiary amines do not exhibit hydrogen bonding, unlike their slimmer cousins, primary and secondary amines. So that will affect various physical properties, solubility, boiling point, melting point being the main ones. Obviously, it affects their interactions with other things in terms of polarity as well, but for this, we're just looking at the physical properties. So what effect will it have on the boiling point? The boiling point will be lower because it can't hydrogen bond, therefore it's not strongly held to other molecules, so it's easier to melt and boil. It will also reduce the solubility in water. Why is that? Because water can hydrogen bond. So if we're introducing something that cannot hydrogen bond, it's not going to selectively bond with those molecules, because we match polarities together. So hydrogen bonding things dissolve well in other hydrogen bonding things, like ethyl-methylamine, for example, would be much more soluble. So therefore, this has a lower solubility and a lower boiling point when compared to this. So the answer must be D in that situation. For question 13, which of the following does not exhibit hydrogen bonding between its molecules? A continued theme of hydrogen bonding here. So straight off the bat, we can say that the answer is D. That should be your instinct. Why? Because you should have memorized that ethers, like ethoxyethane, do not exhibit hydrogen bonds. Why is this? Because for whatever carbon group is bonded to the oxygen on one side, there will be another one on the other side. This means there is no direct oxygen to hydrogen bond. Okay, for hydrogen bonding to be present in an oxygen containing molecule, okay, this bond has to be present. And what I would really encourage you to start doing is thinking about hydrogen bonding, PDPDI, LDFs, etc., as a presence based on the bond itself, not the individual elements. Hydrogen bonding is not based on the presence of that, it's based on the presence of that. It's the difference between the potentials of two particular points in a molecule, as in the electronegativity differences between two bonded points within a molecule. Okay, so that's important. If we then just track that onto A, B, and C, ethanol has an OH bond, hydrogen bonds. Ethylamine has a nitrogen to hydrogen bond, which also is appropriate in terms of electronegativity differences for hydrogen bonding. And ethanoic acid contains an OH bond as well. So they all hydrogen bond. But you should just know that from your general knowledge at this point anyway. 14. In the homologous series of amines, this is all about amines, this page, an increase in chain length is accompanied by what in terms of volatility and in terms of solubility in water. Okay, as we get bigger, okay, it's harder for these molecules to end up in the gas state. Why is that? Because there's more intermolecular forces between molecules because they're bigger. So it won't be as volatile, so it would show a decreased volatility. It also wouldn't be as soluble in water because as we increase the chain length, regardless of primary, secondary or tertiary amines, as in regardless of if they initially hydrogen bond or not, if I then increase the chain length of carbon and hydrogens by 1, 2, 3, 4, 5, 6, however many carbons are like in the chain, it will then decrease the polarity. Why? Because I'm adding a big non-polar chain. Hydrocarbon chains are non-polar, remember. So the bigger the carbon to hydrogen chain is, the lower the solubility is in something like water, which can hydrogen bond. So decrease and decrease. So for 14, the answer should be B. Move on. 15 is some functional group interconversions. So you're given a table of 4 substances and you're asked to identify a reaction sequence. So this is a situation where you have to go sort of from A to B to C to D kind of thing. And you've got to surmise what reactions were used to do that. Now what's important is for you to have a confident approach for these questions. For me, I would be looking for sort of indicator species, if you like, to use a biology term. So something, for example, that stands out to me is the fact that this involves an addition reaction at the end. I'm starting at the end because I can. I don't need to start at the start, as long as I get the right answer in the end. And actually in industry, they would usually do this in a synthetic lab. It's called retrosynthesis. They would usually take a molecule that they have and they would work backwards to figure out maybe where it came from. Now, I'm not doing this because I'm in a synthetic lab. I'm doing this because addition reactions obviously have to involve something with a double bond. So straight away, I can clearly indicate that substance number 4 must be present for the reaction of Y to form Z. Therefore, substance Y must be substance 4. There is no argument about that because substances 1, 2 and 3 do not have a carbon-to-carbon double bond, so cannot do an addition reaction. So straight away, Y is 4 gives me one answer. It's C, and that's that. I'm quite confident to leave that question at that. However, I'm not going to do that. I'm going to explain why that's correct. So just to make sure, I'll go through it now piece by piece. That means, if we select that, compound W must be 3, and then we're going from 3 to 2 to do the reduction reaction. Does that make sense? Well, in 3, I've got a ketone, and in 2, I've got a secondary alcohol. That makes sense. If I go from a ketone to a secondary alcohol, I've completed a reduction reaction, and the opposite would be oxidation, of course. Also bear in mind what the reagents would be at each case here. That's good revision for us as well. Going from a ketone to a secondary alcohol, I would need to use something like lithium aluminium hydride to do that reduction. Then going from X to Y, I'm arguing that I'm going from 2 to 4, so here to here. We're arguing that that's a dehydration. I would agree. To get from here to here, I'll need to remove a mole of water. Okay, a hydrogen from the end and the OH from the middle. That makes sense. And then lastly, as we've already discussed, we go from 4 to 1, doing an addition reaction of clearly HCl to add a Cl across here and a hydrogen across there. So the answer is definitely C for 15. For 16, which of the following statements about benzene is not true? Okay, well, we'll just go through them. Is it planar? Yes, it is. It's a flat molecule because of the delocalized electronic system. Is it susceptible to attack by electrophilic reagents? Yes, it is. It's the only reaction that you should remember that you can do directly onto a benzene ring is electrophilic substitution. Its carbon-to-carbon double bonds, are equal in length. Yes, that is true, which is why the Kekulé model is not appropriate for us right now, but rather we use the model with the delocalized system of pi electrons to indicate that each of these bond lengths should be symmetrical. It's readily attacked by bromine. That is not true. Why? Because there's no double bonds present technically in that molecule. So it can't undergo addition reactions, therefore it cannot be attacked by something like bromine, which would have to undergo nucleophilic substitution or electrophilic addition. So even though it's electrophilic, benzene molecules do not undergo addition under most circumstances. Any circumstances at advanced higher level, but under extreme conditions, like some kind of UV reactor or something, we can maybe get it to do it, but that is not for us right now. So the answer is no for that one. So 16 should be D. Question 17, nice and easy hopefully. Salbutamol is used to treat asthma. It behaves like the body's natural active compound by triggering a response in the muscles of the airways. Therefore, it is acting as an agonist. That is just a definitional question. You either knew that it mimicked the body's natural response and behaved like an agonist, or you didn't. Okay. An inhibitor is not something that we deal with. A receptor is an area of the body that it receives something in some way, and an antagonist was the opposite answer to agonist, where it would block the body's natural response, which clearly is not what salbutamol is doing in this case. Okay, some analytical stuff at the end here. 18. Which of the following splitting patterns would be observed for the circled atom in the high resolution 1H NMR spectrum of ethanol? So what does that mean? Well, there's a lot to unpack here in terms of the full NMR spectrum that would be derived from this molecule, but we're just going to focus on the high resolution part, which is to say what is the multiplet that would be seen from a given hydrogen environment. So if we are here on this hydrogen environment, we will receive signals from a neighbouring hydrogen environment. What does that mean? It has to be close in terms of proximity to this proton, and it has to be on a different environment. So straight away, I can get rid of that top one there because it's the same environment as this bottom one. So I'm not going to receive a multiplet signal, right? A sort of echo from a neighbour from something that's not a neighbour, right? So I'm needing to look to the next nearest hydrogen environment, which is this one. There's 1, 2, 3 protons on it. And then if I use my little rule, I need to add on a signal for every set of hydrogens that I have. So if I've got a set of 3, I'll add on 1, and that should give me a quartet signal for those 3 protons in the neighbouring proton environment. Notice that I'm using protons synonymously with 1H. Okay, question 19. Again, it's just looking at the data, but really, we're given a relatively simple molecule with clear functionalities. We've got a benzene ring, we've got a double bond, we have got some kind of ether, and then we've got some kind of hydroxyl. This is called eugenol. The infrared or IR spectrum of eugenol would not be predicted to have an absorption in the wave number range of what? Stereotypically, this one here is what we would see if we had a carbon to oxygen carbonyl double bond. Now, whether that would be an aldehyde or a ketone carbonyl or a carboxylic acid carbonyl, it doesn't matter. There is neither of them present. Therefore, we wouldn't expect to see that characteristic signal. It's as simple as looking up the predicted ranges or values for this, for this, for this, and finding that matches to these 3 other answers. That's the other way to do that question. But this wave number range, should stand out to you at that point. Okay, lastly, this one was quite cheeky actually. So what do we have to do here? 200 centimetres cubed of water is added to a solution of sodium hydroxide. Initially, that solution is a volume of 50 at 2 moles per litre. So we have a volume and a concentration. The way that I've said that should indicate how we're going to approach this question. But anyway, the concentration of the diluted solution is what? So first of all, if we're going to work out anything based on this initial solution, right, just like we would do with standardisation, we need to take account of the number of moles that I have. I can't start working between solutions until I've got something to work with. So if I'm working out the number of moles, I need to work out C times V in this case, which for this question would be a concentration of 2 times a volume of 0.05. So if I do that in the calculator just now, that gives me, that's quite difficult to see there, a concentration of 0.1, or sorry, a number of moles of 0.1, and that is my base solution. Now, if I dilute that with 200 centimeters cubed of water, physically, let's think about what is being done. I'm taking 50 centimeters cubed of solution, and I'm adding 200 centimeters cubed of water. So in total, my solution volume is going to be equal to 250 centimeters cubed. My number of moles, right, within that solution of sodium hydroxide specifically has not changed. The same number of particles that are ions of sodium and hydroxide that were contained in here are still contained in here. It's just that there's some extra water floating around. So the number of moles hasn't changed. The volume obviously has changed, but the impact will be had on the concentration value, which is what I'm asked to figure out. And that's why I needed the number of moles. So I can use these, of course, in that ratio there. I can take 0.1, I can divide it by my new volume in litres, 0.25, which I'll do now. And that gives me 0.4. And so the answer then for 20 is B.